Today we'll discuss all the problems from the latest Codeforces Round, Division 2. Starting with problem A, you can read it now or listen to my explanation. In my explanation, you are given two integer numbers L and R. You have to find an integer number between L and R, which has the maximal possible difference between its maximal and minimal digits. The solution is really simple, so let's just consider numbers L, L plus 1. Try every number, L plus 2, until we either meet R or L plus 100. Because if we match L plus 100, let's look. If our L was, suppose, 3, 1, 4, 7, something, let's consider the last two digits. If we considered 100 numbers, the last two digits have made a full circle. So we've made all the possible combinations of the last two digits, including, for example, 90. Which means that we have already met the maximal possible difference, and it's no point in going further. So we can stop there. Let's look at the implementation. So this f is just a function which returns the difference between maximum and minimal digit in the number. Initially the answer is L, the answer difference is f of L. We try starting from L plus 1 up to either R or L plus 100. That's it. Moving on to the problem B, you can read it now or listen to my explanation. In my explanation, you are given n arrays of the same length m. Then for every pair of those arrays, you take the sum of absolute values of the differences between the corresponding elements of those two arrays. And then you sum up such values by every pair. You need to output that sum. Before we start solving, let's agree to call the absolute value of difference, let's call it distance between two numbers. Let's write down the sum that we want to calculate. And let's regroup this sum. So now you can say that you first pick a column, and for that column you take the sum of distances for all pairs of values in that column. So let's solve this problem individually for each column. Now you can list all the values that occur in this column and sort them. And now the problem sounds like this. In a sorted array, you need to find the sum of all pairwise distances. So let's draw this array as points on a line. Each value is some points on the coordinate line. And let's draw those pairwise distances. Each of such distances can be presented as a sum of smaller distances. But let's for each small distance find how many larger distances will it be a part of. For example, for such distance, it will be a part of such distance, of course, then such, and such. You can express the exact amount of distances which that distance will be a part of by saying that you have to just fix the left point and the right point. In this case, the left point can be chosen two ways, and the right point can be chosen in three ways. So there are 6 distances which that distance will be a part of. Of course, we can easily calculate this for every neighboring distance, and then just multiply this distance by the number of times it will be a part of a larger distance, and sum up all such values, and that will be our answer. Let's look at the implementation. So here I initially read this array having columns and rows swapped. So my first coordinate is j and the second coordinate is I. Then I fix a column, I sort its values, and then for every neighboring pair, I take the distance between this neighboring pair times the number of ways to pick a point left of this pair times the number of ways to pick a point right of this pair. And then I sum it all up and output. Now for the problem C, you can read it now or listen to my explanation. In my explanation, you are given, again, two integer numbers L and R, and you have to find an integer number between L and R such that it has the smallest possible difference between its maximal and minimal digit. For the purpose of that problem, we will consider our numbers as strings of digits. Let's express the fact that one number is less than another in terms of strings. So first of all, A is less than B if its length is less than the length of B. But if the lengths are the same, then in some position A and B must be different. And if you look at the first such position, so here A and B are the same, but the first position when they are different, digit in A must be less than digit in B. Now if this is our number L and this is our number R, first let's consider a case when length of L is less than length of R. It means that if we replace every digit in L with 9s, then such number will be between the initial L and R. And it will have the minimal possible distance between maximal and minimal digit, so we can just output this number as an answer. Let's also consider a case when L is equal to R, then we just output L. Now L is less than R. It means that several first positions are the same, maybe 0 of course. But the first position when they are different, L must contain a digit smaller than R does. So how can we express the fact that our number must be between L and R? Let's split such numbers in several categories. First two categories will be just L and R. So first two cases is when n is equal to L or n is equal to R. Let's just consider those cases. Now let's consider n's which are strictly in between L and R. Again, let's say those prefixes of L and R coincide, and this is the first position where L and R are different. Obviously, this prefix of n must also coincide with L and R, but then let's consider three cases. First case is if this digit of n is different from both L and R, then it must be strictly between these two digits. If it's true, then all of those digits in n may be arbitrary, so we have full freedom of choice regarding what to put here. The second case is if several first digits in n starting from this position coincide with L. But then this digit must be strictly larger than the corresponding digit in L. And then the remaining digits may be again arbitrary. And the third case is analogously if several first digits of n starting from this position coincide with the digits in R, and then the next digit is strictly less than the corresponding digit in R, and then the remaining digits may be arbitrary again. So let's find the best n of the last type that I described. The remaining types will be covered analogously. For this type of n, when the first several digits coincide with R, let's just fix how many first digits do coincide with R. And then for this position, let's fix which digit exactly stands on this position in n. For example, let's say it's 3. Now you have already some digits fixed here. And of course, for those positions, you just make them equal to this digit, for example. This way, all those digits will be already in between the minimal and maximal digit in here. So you just need to find the distance between maximal and minimal digit in here and update the answer with such candidate. And you do it for all possible lengths of prefix that coincide with R and for all possible digits here. And then you do the same in all other cases. Let's look at the implementation. This function returns the maximal digit in the prefix of a string. And this function returns the minimal digit in the prefix of a string. First, I transform L and R into strings, which I call A, B. Then I check if they have different length. I just output all 9s. Then I find the first position where A and B are different. If such position doesn't exist, I just output A. Then my first candidate for the answer is A, and its score is this. Then I update the answer with the candidate of B and its score. Here I cover the case when my number coincides with L first. So here I fix the first position where it's different from L. Then I fix precisely the digit which will stand on the next position. Then I find what is currently the minimal digit that I've fixed and the maximal digit that I've fixed, and update the answer with such score. And if the answer score is improved, then the new answer is just A, but starting from this position to the end, all the digits were replaced with D. Then I do the same for the case when it coincides with R first. And then the last case is when it doesn't coincide with L or it doesn't coincide with R. So the very first digit is different from both L and R. Then I fix this very first digit between the first digit of L, starting from this position of the first difference, and the very first digit in R, starting from this position. And then I do all the same thing, and I output the answer. That's it. Now the problem D. You can read it now, listen to my explanation. In my explanation, you are given an array A of length n and an odd integer number k. For every subarray of A of length k, you take the minimal number of elements that you need to change to make this subarray a palindrome. Then you sum up all such values over all subarrays of length k, and you need to output that sum. Let's consider some subarray of length k. In my illustration, k will be 5. You need to add 1 to the answer for such pair if those values are not equal, and for such pair if those values are not equal. Then you consider such subarray, and you will need to add 1 for such pair if it's not equal, and for such pair if the values are not equal. Then you will add 1 for such pair if they are not equal, and for such pair if they are not equal, and so on. Let's first consider an n-squared solution, which we will later optimize to something faster than n-squared. We will fix a position I and look at all the edges that I've drawn which go to the left of I. And for each such edge, we'll add 1 if the corresponding element on the opposite end is not equal to A of I. To optimize this solution, we need to realize that those elements will be always just elements on either even positions or odd positions on some subsegment. Let's express this subsegment explicitly. So suppose I fixed a position I. For which position j do I need to compare A of j to A of I? Let's say that C is the center of this subarray, where I and j are the mirrored pair. It means that j is equal to C minus I minus C. So j is equal to c minus I. Let's see which values can C take. C must be at least k over 2 rounded down if we have zero indexation in our array, and no more than n minus 1 minus k over 2 rounded down. Let's multiply all of the sides of this inequality by 2 and subtract I from each part. We'll get 2 times k over 2 rounded down minus I is less or equal than j, because 2c minus I is j, less or equal than 2n minus 2 minus 2 times k over 2 rounded down minus I. So on one hand, j must occupy this range. On the other hand, j must be just not negative and less than I. So j must be no less than the maximum of these two and no more than the minimum of these two. And of course, j must have the same parity as I, because c must be integer. So now the remaining problem sounds like this. We have a sequence of queries. For each query, we want to take elements on either even positions or odd positions of some subsegment and tell how many of them are not equal to some value x. Instead, let's just answer the opposite query. How many values on either even or odd positions of subsegment are equal to x? In order to do that, we will build vectors which I call where. It will be a 3D vector. The first two parameters of that will be either 0, 1 for the parity and x for the value. So this will be a list of either even or odd positions where x occurs for every value of x. Values of x are quite small, so we can do that. If they were larger, we could just initially compress the coordinates as well. To build such vectors, you just need to go through every position in your array, and when you occur some ai, you just push back I into the vector where of I%2 ai. Push back I. As you go from lower I to higher i's, those vectors will be already sorted when you build them. So for every value and for every parity, you know all the positions in your array where such value occurs on such parity. Now to answer a desired query, we just need to address to one of such vectors and tell how many positions from this vector are from L to R. But this is the same as just asking how many values in a sorted array are from L to R, which can be answered using just two binary searches, by L and by R. That's exactly what we do in the code. Let's look at the implementation. And here, just for every I, starting from 1, because for 0 there are no previous j's, I write out those inequalities again. I form the left border for j and the right border for j. If the left border is larger than the right border, I simply skip such I. Otherwise, I make the right border uninclusive. I take the corresponding vector, so I want the j to have this parity, and I want the value to be this. Eq is the number of equal values on such parity in this subsegment. So I just do lower bound of R minus lower bound of L. And then I take the overall number of positions of this parity in such range minus the number of those that are equal. So this will be the number of those positions which are not equal to AI. I add this to answer and output the answer in the end. Now for the problem E. You can read it now or listen to my explanation. In my explanation, you are given three integer numbers, n, k, and m. You have to find the number of arrays of length n with values from 0 to k minus 1, such that one of its values is equal to the sum of all other values modulo k. So in this problem, we work with modulo k arithmetics. Each value is the remainder modulo k, and one of the remainders must be equal to the sum of all other remainders in the array. You need to find the number of such arrays of length n modulo m, where m is just some large prime number given in the input. There were three versions of this problem. Different versions had different constraints. But we will discuss only one solution which will work for all of those versions, and moreover, it will work for any k less than m. The time complexity of the solution that we will discuss will be O of log n plus O of log m. So first of all, let's rewrite this statement. If some value on the position I is equal to the sum of all other values modulo k, it means that it's equal to the sum of all values minus itself. So it means that the sum of all values is equal to 2 times ai modulo k. Let's first solve this problem for the case of odd k, because it's easier this way. If k is odd, we can safely divide by 2 modulo k and get a valid result always. So for each such remainder, there will be exactly one such remainder. And for each such remainder, there will be exactly one such remainder that multiplied by 2 gives this remainder. So let's call this remainder R. And let's calculate all the good arrays which have the sum exactly to R. As I said, each to R will be a unique remainder, so each such good array will be calculated exactly once. So once again, we need to calculate the number of arrays of length n which have the sum to R modulo k, and such that at least one of the values is equal to R. First of all, let's calculate all the arrays which have the sum exactly to R. We will calculate it using a combinatorial process. We'll fix this value. We'll have k choices. We have k choices for this value, and so on. We'll fix every value one by one until we arrive to the last value. And for this value, we'll set exactly the value we need to make the sum equal to 2R modulo k. So we will have only one choice. Thus, we had n-1 steps, and on every step, we had exactly k choices. So the number of such arrays which have the sum equal to 2R modulo k is exactly k to n-1. Now let's subtract those arrays that do not contain the value R, because we only wanted to calculate those that have the sum to R and contain the value R. So now let's calculate those that don't contain the value R, and we will subtract their amount from this, and this will be the number of such good arrays. We'll calculate such arrays that don't contain R and have the sum exactly to R using a similar process. We'll fix a value on the first position. This can be any value, but now we have k-1 choices because we don't want to use the value R. Same on the second step, and so on. And for the last value, we will fix exactly the value we need to make the sum to R. The number of such processes is k-1 to n-1. But you could spot that on the last step, the value that we needed to add to the sum to make it equal to R could be exactly R. So we also calculated such arrays where this value is r, while we only wanted to calculate the arrays which don't use the value r. So we need to add back those arrays that we mistakenly subtracted. So those that result in r on the last step. In order to do that, let's fix that the last value is r, and let's calculate the number of such arrays that don't use r on those positions, but have exactly the sum of 2r. We'll again do a similar process, but this time we'll stop not there, but here. We'll fix all those values, but then we'll stop on this and make it equal to exactly the value we need to make the sum equal to 2r. Number of such processes is k-1 to n-2 now. But we again run into the same problem. This value that we added to make the sum of the whole array to r could be r again, while we wanted to calculate only those arrays that don't use r on those positions. So we need to subtract back those arrays that we've mistakenly added back. So it's those arrays that don't use r's here, but that end on 2 r's in a row. So let's again fix the 2 r's on the end and do the same process, but this time we'll stop even earlier. We'll stop here and set this value to the exact value that we need to make the sum equal to r. Again, the number of such processes is k-1 to n-3. But again, if this value is r, we need to add back those arrays that we've mistakenly subtracted. So this logic will continue. We'll add back k-1 to n-4, then subtract k-1 to n-5, and so on, until in the very end we'll want to either subtract or add those arrays that end on n-1 r's in a row, and they don't use value r on the first position. We'll calculate such arrays using the same process. We'll have 0 choices now, so it's k-1 to 0, and then we'll set this value to exactly the value we need to make the sum to r. But finally, if this value turns out to be r, we need to cancel this last operation by adding or subtracting 1 back. I'll put this minus plus 1 in figure brackets. It means that I only add this term if the last value here turns out to be r. So it's only for such r that nr is exactly 2r modulo k. So I'll later calculate the number of such r's that satisfy this equality, and I'll add or subtract 1 for each such r. But for now, let's focus on this part of the expression. You can rewrite it as k to n-1 plus minus the sum from 0 to n-1 negative k-1 to the power of I, which is equal to k to n-1 plus minus sum of 1 minus k to the ith power from 0 to n-1, where this plus minus is the same sign that was used here, because 1 minus k to 0 is 1, and it must have the same sign as it has here. But we know from math that this sum can be expressed as just 1 minus k to the nth power over 1 minus k is equal to 1 minus k to the nth power over k. This is just a formula for the sum of geometrical sequence. If you don't know, you can Google it up. So we know that for every remainder, we need to add these two answers. K to n minus 1 plus minus, depending on the parity of n, plus or minus 1 minus k to n over k. So the overall effect of this expression on our sum over all remainders will be this times k, which is equal to k to n plus minus 1 minus plus 1 minus k to n. But now we also need to add or subtract 1 for every such remainder that satisfies this condition. But let's just find how many such remainders there will be. So this condition can be just expressed as n minus 2r is 0 modulo k. So n minus 2r is divisible by k. Let's say that d is the greatest common divisor of n minus 2 and k. So let's divide them both by their greatest common divisor. Now this part is coprime with this part. So if this is divisible by this, it means that just r is divisible by this. And the number of remainders of k which are divisible by k over d is k over k over d, which is just d. So we will later need to either subtract or add d, which is the greatest common divisor of n minus 2 and k. We'll subtract and add depending on parity of n. That's it for the odd case of k. Now for the even k. For the even k, the solution will be actually very similar. But first we need to deal with this. If we fix the sum of our array, let's call it S, there will be two possible remainders that multiplied by 2 give the remainder S modulo k. And moreover, those remainders will be different by exactly k over 2. So let's just call smaller of those two remainders r, and the larger will be r plus k over 2. And now S can't be any remainder. S will now only be an even remainder. So let's fix the value of r, but now r is not an arbitrary remainder, r is a remainder from the first half of the remainders. We again will want to find the number of good arrays that have the sum exactly 2r modulo k. But now good arrays are those that will contain either r or r plus k over 2. So let's again try doing the same thing. First of all, let's calculate all the arrays that will have exactly the sum 2r, and it will be the same k to n minus 1 because of the same reasoning. But then we want to subtract those arrays that don't use r or r plus k over 2. So we'll again use the same process. We'll fix all those values, but in each step, we'll have k minus 2 choices now. So it's k minus 2 to n minus 1. And when we set the last value, exactly the value we need to make the sum equal to r, now there are two problematic cases if this value turned out to be r or r plus k over 2. Both cases are the cases that we subtracted, but that we didn't want to subtract. So we need to add them both back. Let's just build such cases that we want to add back using such process. On the first step, we fix this element. Now we have two choices, r or r plus k over 2. then on all those steps up to this position, we'll have k minus 2 choices. And here we'll have no choice. We'll have to make this element exactly what we want to make the sum equal to 2r. So if this element turned out to be also r or r plus k over 2, then we need to subtract such arrays that we've mistakenly added back. Let's again calculate such arrays that end on 2 values, each of them is r or r plus k over 2, that have the sum exactly to r, and that don't use neither of those values on the previous positions. Again, we will use the similar process. We'll first fix what this value is equal to, then fix what this value is equal to. We'll have 2 choices here, 2 choices here. Then we'll have k minus 2 choices to pick the value for this position, and so on. We'll stop here, and we'll make this exactly what we need to make the sum to r. So we'll subtract 2 to the second power now, times k minus 2 to the power of n minus 3. Obviously, this will continue, so now we want to add back those cases when this element turned out to be r or r plus k over 2. So it will continue. The power of 2 will always increase, and the power of k minus 2 will always decrease. Until on the very last step, we want to either add or subtract the number of such arrays that end on values r or r plus k over 2 on all those positions, except for the first position. But the first position is not r, neither r plus k over 2. So we'll count such arrays by the same process. We'll first fix n minus 1 values for those positions, each time having 2 options. Then we'll have 0 choices on this prefix, and then we'll have only 1 choice for this case. So in the end, we'll just add or subtract 2 to the power of n minus 1. But again, similarly, if this value that we had to pick to make the sum exactly to r was r or r plus k over 2, then we need to subtract or add the number of such arrays. So we need to subtract or add the number of such arrays that consist only of values r or r plus k over 2 and that have the sum of exactly 2r. To calculate the number of such arrays for a given r, let's suppose that exactly a of all values were r plus k over 2, and n minus a values were just r. So in such case, the sum will be n times r plus a additional times k over 2. This must be exactly 2r modulo k. So let's rewrite it as n minus 2r plus a times k over 2 must be divisible by k. Well, first of all, as this is divisible by k over 2, this must be also divisible by k over 2, because the sum must be also divisible by k over 2. So the first constraint is that n minus 2 times r must be divisible by k over 2. And I remind you that r is from 0 to k over 2. But if this constraint is satisfied, then this is either k over 2 times some odd factor or k over 2 times some even factor. Depending on if it's odd or even, a must be also odd or even, must have the same parity as this factor. So if for the specific r this constraint is not met, then we don't add anything for this r. But if this constraint is met, we need to subtract or add number of such arrays where all the values are r or r plus t over 2, where the number of those that are r plus t over 2 is even or odd. So it's just the same as asking for the number of sequences of length n of zeros and ones. How many sequences have an even number of ones? And how many sequences have an odd number of ones? Because for each time I put r, I can put 0 into the sequence, and for each time I put r plus t over 2, I will put 1 into the sequence. But obviously the number of sequences that contain even number of ones and the ones that contain odd number of ones is the same. Because for each such sequence, I can put into correspondence such sequence where the last value is just inverted. And of course, those two sequences will have a different parity of the number of ones. So I split all the sequences in such pairs where one has even number of ones, one has odd number of ones. So obviously, there is a bijection between those two. So obviously, the number of those that contain even number of ones and the ones that contain odd number of ones is just the half of all sequences. So it's just the half of 2 to the power of n. So it's 2 to the power of n minus 1. So I need to add or subtract 2 to the power of n minus 1 for each such r that satisfies these conditions. And let's find the number of such r's. Again, let's say that d is the greatest common divisor of n minus 2 and t over 2. Let's divide them both by d. As this is coprime with that, we can get rid of this part. So r must be divisible by k over 2d. The number of such remainders among the first k over 2 remainders is obviously k over 2 over k over 2d, which is obviously just d. So again, the number of such remainders for which we want to subtract or add 2 to the power of n minus 1 is just the greatest common divisor of t over 2 and n minus 2. So we'll add them or subtract in the end. For now, let's just focus on this sum. So without this part in the figure brackets, I can again rewrite the remaining expression as k to n minus 1 plus minus sum for I from 0 to n minus 1 2 minus k to the power of I times 2 to the power of n minus 1 minus I, where again this plus minus is the same as this plus minus, which we can again express using the formula for the geometric sequence. Plus minus 2 to the power of n minus 2 minus k to the power of n over 2 minus 2 minus k, which is again k over n minus 1 plus minus 2 to the power of n minus 2 minus k to the power of n over k. If you sum up all such expressions for every remainder from 0 to k over 2, you'll get that times k over 2, which is k to the n over 2 plus minus 2 to the power of n minus 1 times k minus plus 2 minus k to the power of n over 2. And then, of course, minus plus 2 to the power of n minus 1 times the GCD between n minus 2 and k over 2. And that's the solution. Let's look at the implementation. So first I have binary exponentiation modulo mod. Then this function returns the modulo inverse for a modulo mod. And basically I just read the integers, and for odd case I apply one formula, for even case I apply another formula. The only thing worth mentioning is that actually you need modular inverse only to divide by 2. As long as modular is odd, which large prime number will of course be, you can find this inverse of 2 by just taking mod plus 1 over 2. So actually, now that I think of it, our solution works even for non-prime modulus. So if you get rid of this inverse of 2, the solution will work purely in O of log of n, because binary exponentiation to the power of n, of course, takes log of n. That's it for today. Thank you for watching, and I remind you that I give private lessons on competitive programming. If you're interested, contact me on Telegram. Goodbye.